This is a tutorial on relations and functions. There are many ways to show a relation. So let's look at this example and we'll discuss how we can show the relation in many different ways. Joe has a fantasy football team. In his first week, his team scores 68 points. In week 2, he scores 74 points. In the third week, he scored 84, and in week 4, he scored 97 points. Now, a popular way to show this relation is in ordered pairs. It's basically putting each value together in parentheses. So 1 and 68, week 2 and 74 points, week 3 and 84 points, and week 4 and 97 points. Another way to show this relation is to put it in a table. So in week 1, put 1, week 2, 3, and 4 in the week column. And then next to the 1, we scored 68 points. In week 2, we scored 74 points. 384. And in week 4, we scored 97. Similar to a table is a mapping diagram. Here you put all your week values in again. 1, 2, 3, and 4. And then your point values 68, 74, 84, and 97. Then the last step for a mapping diagram is to draw a line connecting the relation. So in week 1, there was 68. In week 2, there was 74, 3, 84, and 4, 97. The last way to show a relation is to graph it. So we'll start with the first order pair, 168. We go to the x-axis, which shows the week. It's week 1, so we come up from week 1. And then we scored 68 points, so we go from 68 points on the points axis, or the y-axis. And then where these would connect is our point. Same thing for week 2. We come up from 2 on the week axis and 74 on the points axis. And you draw another point. Same thing with week 3. From 3, we go up to 84, which is about there. And for the fourth one, we come up from week 4 and go to 97, which is right there. Now that we know how to show or illustrate a relation, we need to talk about domain and range. The domain is simply the first point in every relation. So in the ordered pair set that we have, our domain would be 1, 2, 3, and 4. And then our range would be 68, 74, 84, and 97. In the mapping diagram, our domain again is our first points, so these would all be our domain, and these would be our range. And then on the graph, it's every point in our graph that has an x coordinate. So it would be all of these points. And then our range is every point on the graph that has a y coordinate. So it would be all of these points. So let's write down the domain and range for each of these examples. The domain, which is usually written as a D, and then the values are put in brackets. Our domain would be 1, 2, 3, and 4. Our range would be 68, 74, 84, and 97. Our domain and range for the next example, the mapping diagram, our domain would be just all the points in the left side of the mapping diagram. So 7, 8, 9, and 10. And our range would be -2, -4, and 8. Now don't be afraid that this range value has less numbers than the domain. This is because according to our mapping diagram, the values of 9 and 10 in our domain both correspond to 8 in our range. Our last example, the graph, the way to find the domain and range. Again, the domain is every point in our graph that has an x value. So if we came up from anywhere on the x-axis, would we run into our graph? Well, the only points that we run into our graph on the x-axis are between 1 and 4. So the way to write your domain is to say that 1 is less than or equal to x, because we're along the x-axis, which is also less than or equal to 4. This means that our domain is every number between 1 and 4, including 1 and 4. Our range is found the same way, except you come from the y-axis. So every point that has a y-coordinate. The only points that have a y-coordinate on our graph are the points between 1 and 3. So we would write our range, 1 is less than or equal to y, because we're going along the y-axis, which is also less than or equal to 3. This means that our range is every number between 1 and 3, including 1 and 3. Now that we understand domain and range, we're going to talk about functions. A function is a special type of relation where every domain value has only one corresponding range value. So let's look at our 6 examples and see if these are functions. Our first one, 2 corresponds to -9 and -4, where 4 corresponds to -4, 6 corresponds to -3, and 8 goes with 7. This one is not a function because 2, our domain point, has 2 range values associated with it, which would make it not a function. Let's look at our next mapping diagram. Here, 4 goes with -2, 5 also goes with -2, 6 goes with -1, and 7 goes with 0. This one is a function because every domain point has only one range value. Now, both 4 and 5 have the same range value, but that's okay. As long as 4 and 5 have only one range value for them, then it is a function. So let's look at our first graph of the straight line. Let's think about how we calculated our domain before on the other graph. Every point on this graph that has an x value is its domain. So if I come up from this x-axis and I intersect my graph and I go back over to the y-axis, I can find a value. Since each x value has only one y value on this graph, this is a function. Let's look at the next one, the one that looks like a U. If I come up from the x-axis and intersect the graph and come back over to the y-axis, does any x value that I can come up with have more than one y value? And the answer is no. There are several x values that have the same y value. So say this was 4 and this was 2, and they both came up, intersected the graph, and came to the y of 3, this would still be a function because 2 only has one y value, 3, and 4 only has one y value of 3. So this is a function because each x value has only one y value. Now let's look at our chart. Here, 1 goes with 17, 2 goes with 17, 3 goes with 19, and 4 goes with 21. So this is a function because, again, every x value has only one corresponding y value. All right, let's look at the last graph that we have, this u that's on its side. If I pick an x value and I come up from the axis, can I find more than one y value? And the answer is yes. If I come up from the x-axis and I intersect my graph here, I can also keep going up and intersect my graph here, which would give me 2 y values for each x value. So this one is not a function. Now let's talk about dependent and independent variables. An independent variable is typically the domain variable, or x. It's what's entered into the function or equation to get your answer. A dependent variable is typically the range variable, y, or the answer to a function or equation. It is called the dependent variable because its value depends on the values of the independent variable. So let's do a couple examples here and see if we can make this any clearer. Susie studies for several hours so she can score higher on her tests. So what are we measuring here? We're measuring the time Susie spends studying and the score on her test. Now you have to think, is her score dependent on the amount of time she spends studying, or is the amount of time she spends studying dependent on her score? Well, the more she studies, the higher she's going to score. And she usually studies before she takes her test, so her score can't influence the amount of time she had studied previously. So therefore, the score is dependent upon the amount of time that she studied. So time is our independent variable, and score is our dependent variable. Let's do one more example. The faster John rides his bike, the higher he jumps off the ramp. So what we're measuring here is the speed John travels at and the height he gets on his ramp. So is the height he gets off the ramp dependent on the speed, or is the speed dependent on the height? Well, the faster he pedals, the higher he's going to go on his jump. The height he goes on his jump does not affect how fast he pedals his bike. So therefore, the speed is our independent variable, and our height is our dependent variable. Now let's try one more example. Every time Hank forgets his lunch at home, he buys a cheeseburger for $5.50 at the cafeteria. If Hank forgets his lunch every day this week, how much will he spend? So what's the dependent and independent variable? Our independent variable is how often Hank has to buy lunch. Our dependent variable is how much he will spend. So the cost to Frank for forgetting his lunch all week. So let's try to write an equation that shows this. Remember, our dependent variable is typically our answer, so we'll call it y. And our dependent variable is what you tend to enter into the equation, so we'll call it x, which is the number of days he needs to buy lunch. Now, if he spends $5.50 every day he forgets to bring his lunch, then his total cost would be 5.5 for $5.50 times the amount of days he has to do it. So if Hank were to forget his lunch all 5 days this week, then his cost would be 5.5 times x, or times 5 for 5 days, which would be $27.50. Now to write this in function notation, the easiest way to think is take your dependent variable, which in this case is y, and replace it with the f of x notation. So our function would look like f of x is equal to 5.5x. Now the function notation is typically drawn with an f, but it doesn't have to be. You could also make it g of x, or any letter you really choose. You just have to understand what this notation means. And this generally means that this is your dependent variable. Now the reason why the x is inside the parentheses is because this is your independent variable. So the function notation means that your dependent variable is a function, which is why we usually use f, of our independent variable. So if we had decided to call it z instead, this would be f of z is equal to 5.5z. So that's how you write function notation. Now let's try to create an equation from a table. Here we have several x and y values, and we want to try to come up with an equation. So let's look at the first set. How do we get 1, which is our x value, equal to 6? Well, there's several ways. Let's pick the two easiest ones. First, we'll try adding 5, because 1 plus 5 equals 6. And on the other side, we'll try multiplying by 6, because 6 times 1 is equal to 6. Now let's check this idea with the other points. So we have a 2, and a 3, and a 4. Let's add 5 to all of them. Two plus 5 is equal to 7. This is not what we're looking for. We were looking for 12. So this does not work. Same here, this would be 8 and 9. These numbers do not match our 12, 18, and 24. So let's hope the other function works. Let's do 6 times 2, 6 times 3, and 6 times 4. Remember, these are our x values. Well, 6 times 2 does indeed equal 12, which is what we were looking for. 6 times 3 is equal to 18, so it looks like we're on the right track. And 6 times 4 is equal to 24. So it looks like we've figured out our equation. Our y values, which is our 6, 12, 18, and 24, is equal to our x value, which is 1, 2, 3, 1, 2, 3, and 4, multiplied by 6. So our equation would be y is equal to 6x. The last part of our tutorial is evaluating functions. If you remember from our notation, this is our dependent variable, and our x would be our independent variable. And when you see this function notation written like this, where there's a number instead of the x, it simply means that 3 is equal to x, or x is equal to 3. So to evaluate this function, you would simply plug in 3 for x. So it would look like this: 7 times 3 plus 15. Negative 7 times 3 is negative 21 plus 15. So our function of 3 would be equal to negative 6. Let's try these next two. Here we're going to plug in 4 for x, so you'd end up with 1/2 times 4 plus 24. So this would be 2 plus 24. So our function of 4 would be equal to 26. The last problem, we're simply going to plug in 1/4 for w. So 12 times 1/4 plus 6. Well, 12 times 1/4 is 3 plus 6. So our function of 1/4 is equal to 9. And that completes the relation and functions tutorial.